Thank you. Good morning, everyone. My name is Maya, and I work with colleagues Xiang and Professor Blumberg at Rutgers University. My topic today is crystal field transitions of the serum ion in the heavy fermion compound serum hexaboride. The key points of my talk today are that we observed the splitting of the two multiplates of the serum ion in both the luminescence process and the Raman process. The luminescence part has interesting temperature dependence. Furthermore, by group theoretical consideration, we identified the peak we observed. We are grateful for the samples from Dr. Rosa, Professor Bohr, and Professor Fisk. We also thank Professor Hall for the discussion. This project is supported by NSF and DOE. Serum hexaboride has a simple cubic structure. The point group of it is OH. It's composed of serum and boron octahedron, that's shown in this picture. We choose a Cartesian coordinate system to define the scattering geometry we use in this study. For example, XY scattering geometry means that the incoming light is polarized along X direction, while the outcoming light is polarized in Y direction. Despite of its simple structure and composition, it has interesting low temperature ordering phenomena. For example, at 3.2 Kelvin, it undergoes a second-order phase transition from high-temperature ferromagnetic phase to a low-temperature antiferrocortical phase. In the ferromagnetic phase, every serum sets are equivalent. However, in the AF2 phase, alternate serum sets carry different quadruple moments, which are of gamma-5 type. When temperature decreases to 2.4 Kelvin, it undergoes another phase transition into an antiferromagnetic phase, which is also interesting because it has double Q structure. Here is shown a spin configuration which satisfies the double Q requirement. The serum ion has one 4f electron. With spin orbital coupling split into 5 halves and 7 half multiplate. The splitting is around 250 millielectron volts. And the cubic crystal field will further split the multiplates into crystal field levels. Here, the 5 half states is split into gamma 8 and gamma 7 crystal field levels, and the splitting is determined to be 46 millielectron volts. Also, the 7 half states will also be split. According to group theory, split into gamma 8, gamma 7, and gamma 6. Here we use the superscript 1 and 2 to distinguish the crystal field levels from 5 half and 7 half. So there are 2 gamma 8 and 2 gamma 7. Our measurement suggests that the splitting of the 7 half states is around 56 millielectron volts. In order to study the two multiplates, there are two methods. First is that because the 5D band is near the 4f level, so that it's possible to observe them in luminescent process. It's also possible to study them in Raman process. Here we show the secondary emission spectrum taken with spring excitation in XY scattering geometry. We first focus on the luminescence part. The luminescence process is basically, here the dotted line represents the Fermi level. Electrons are excited below the Fermi level into the 5D band, and by relaxation it comes to the 5D band bottom and then drops to lower states with the emission of light. Here it turns out that the two peaks here correspond to exactly the 5-half and the 7-half multiplies. And we also notice that there are fine features here. They are of Raman nature, and the next part we will discuss this. Basically, the Raman process is that the electrons are excited from the ground state to a virtual intermediate level, and they draw back to lower levels. The difference of the incoming light and the outcoming light is the Raman shift plotted here. We identify these three small peaks as with the crystal field level gamma 6, gamma A2, and gamma 7.1. Also notice that there is a sharp peak, which in fact is the T2G fauna of this system. In order to assign these peaks with the crystal field levels, it's helpful to know their relative intensity in different symmetry channels, which I will show now. In order to do it, we need to evaluate the matrix elements of this form. Here I stands for the initial state, and F is the final state. The O is the effective Raman operator. By symmetry consideration, we determined the operators corresponding to the 4 symmetry channels of this system shown here. For example, the operator of the full symmetric A1G channel can only be a constant because of the confinement of the point group symmetry of this system. The EG symmetry and the T2G symmetry are quadruple. Correspond to quadruple transition. Here we express them as the ladder operator of orbital angular momentum and spin angular momentum. The most interesting part is the anti-symmetric T1G channel, which contains both the ladder operator of the orbital part and the spin part. The blue one shown here are the equivalent expression. For example, this L plus, L minus can also be expressed by L minus, L plus. Because we are interested in intensity, so they will give equivalent results. Because T1G contains the spin ladder operator, it's special that it responds to a spin-sleep transition. On the contrary, the A1G, EG, T2G symmetry channels is spin-preserving transitions. Here is a simple example to illustrate how we really evaluate the matrix elements. The initial state is taken from one of the 4 degenerate states of gamma 81 crystal field level, and the final state is taken from gamma 82. The form of the wave functions are determined also by group theory. For example, we use T1G as the effective Raman operator, and we focus on this term and this term. It's saying that the spin ladder operator will change the spin up to the spin down, and this orbital angular momentum ladder operator will increase the Z component of the orbital momentum, so that this Y30 spin up term and this Y31 spin down term will give a finite contribution to the matrix elements of T1G operator. There are 2 kinds of transitions which contribute to the Raman signal. The first is simple ordinary transitions, which means that the electrons are excited from the ground state or at finite temperature from the gamma 7 state to a virtual intermediate level, and then drops back to the corresponding levels. And the second mechanism is transitions by mixing. because of the existence of the qubit crystal field, the rotational symmetry of the system is broad, and in fact the 5-half and the 7-half multiplets have a finite small mixing. It turns out that gamma 8.1 only meets with gamma 8.2, and gamma 7.1 only meets with gamma 7.2. So that the transition, so the gamma 8 transition and the gamma 7 transition will be enhanced by this mechanism. And then I show the results by plotting the normalized relative intensity against all possible transitions. These 4 are from gamma 8.1 state, and these 3 are from gamma 7.1 state. This only exists at finite temperature, and gamma 8.1 is the ground state. We first show the A1G results. As can be shown here, only gamma 8 to gamma 8 and gamma 7 to gamma 7 has a finite intensity. This result is consistent with the requirement of the multiplication table, which determines the symmetry channels where Raman signal exists. For example, as shown in the table, only gamma 7 or gamma 8 has A1. It is possible that Raman signal exists in V1G channel. Similarly, we also calculated the relative intensity in EG, T1G, and T2G symmetry channels. Notice that it's interesting that T1G symmetry channels all has infinite intensities, so that we say that the Raman scattering, not only provides us with the orbital information, but also provides us with the spin information. This is only possible by the strong spin orbital coupling of this system. While this spin orbital coupling is possible to use Raman scattering to access the spin information, and also the symmetry of the excitations are also classified by choosing different scattering geometries. Finally, this is the T2D result. And with this relative intensity, we are now able to identify the crystal field transitions. So we return to the secondary emission spectra with green excitation in XY scattering geometry as shown before. We are interested in these 2 peaks. Because these 2 peaks are right above the broad luminescence peak, it's hard to really determine the relative intensity. So that by changing the excitation from green to blue, we shift the luminescence peak, but the Raman peak are at the same position because the Raman shift is the difference between the incoming and outcoming light. So that if you change the excitation, the Raman peak will stay at the same position. In this way, it becomes like the shoulder of the luminescent peak, which makes it easier to determine the relative intensity. And by measuring in all 6 possible scattering geometries, and we know the relationship between the scattering geometries and the symmetry channels, we can use the previously obtained relative intensity to identify the nature of the 2 peaks. It turns out that the left peak corresponds to, we assign it according to the relative intensity to gamma 8 to gamma 8 transition, and the second peak is the gamma 8 to gamma 6 transition. However, with blue excitation, we still have huge luminescence peak, which may influence the results. To totally get rid of the influence of, to large extent to get rid of the luminescence influence, we also measure with infrared excitation. With infrared excitation, you can see from the vertical axis, the luminescence is almost gone. So that here we observe the new peak here, and we assign according to the relative intensity to be gamma 7 to gamma 8 transition. And this peak is the one we already seen here. is still the gamma 8 to gamma 8 transition. The sharp featured here is the T2G phonon mentioned previously, and this small peak, which is large here, is the gamma 8 to gamma 7 transition within the 5-half multiplexer, which already been seen by previous research. So in summary, we observed the splitting between the multiplexer in both luminescence process and Raman process. The temperature dependence of the 5D band bottom to 7-half multiply luminescence is currently a puzzle to us. And we also identified the crystal field transitions within this system by pure group theoretical considerations. We get the relative intensity, and with the help of the intensity, we can identify all these peaks. Thank you.
Okay, questions? Yes.
Very stupid question. So, how do you know you see the transition 7 to 8 and not 8 to 7 or vice versa?
Sorry, I can't hear you clearly.
How do you know that you see the transition from, let's say, gamma 8 to gamma 7? And then not from gamma 7 to gamma 8?
Oh, because we know the because it's already determined that there is around 46 millielectron volt splitting here, and this splitting is around 250 millielectron volts. And we also have the Raman shifts to make the energy consistent. It cannot be this one, but this one, so that the energy is consistent with our measurement results.
I guess your question was, how do we know that the gamma 7 is not a ground state, gamma 8? The question is about which one is a ground state.
This is determined by previously, for example, for many methods, neutron scattering, Raman scattering, and also
None of them will tell which one is the lowest.
also NMR experiment.
But I think at the time there was, we said there was a splitting of ground state and
There was a proposal that there is a Young-Teller effect which will split the gamma 8. But I don't think the data is consistent because this gamma 8, gamma 7 transition remains sharp in Raman.
Keith, what happens to the strength of the Raman signals when you go from IR to visible excitation? Does the Raman scattering get stronger when you're near the resonance? I'm basically asking if there is any significant coupling between the Raman excitation and the electronic excitation, like resonance enhancement of the Raman scattering.
In fact, those luminescence is strongly increased when we
Of course.
luminescence.
Yes,
The
of course.
Raman signal essentially are the same.
I see. Okay.
The intensity of
Okay.
Well, in essence, the height of the peak, I guess with blue and red or green, is still going to be higher than this 0.4 units.
No, but it's arbitrary units. Are those,
No, those are
Those scales really
those
don't
scales compare, yeah. They are not that.
Yeah. They're not absolute relative to each other.
They are relative to each other. Their calibration has been used.
Yeah. Should there be any coupling?
No, of course, resonance. Yeah, resonance Raman is enhanced, and of course it's very challenged.
No, but that depends on the coupling to the electronic
No.
transition.
It's a second order perturbation, so there's a denominator which orders the response.
Well, yeah.
Right, but on top of that, the important point here is that this T1G excitation, which is very unusual. It's antisymmetric again. It's similar to this A2G stuff that I spoke yesterday about. It's only possible in resonance regime. It's fundamentally impossible if there is no resonance intermediate state.
It's kind of vibration.
Okay, let's thank the speaker again. So running a little